So friends, in this section, we are going to talk about a sphere and a spherical shell. Now, sphere in our day-to-day life has a plethora of examples. A football, a volleyball, generally all sorts of balls, and for that matter, even the earth has a spherical shape, right? Anything which is circular and solid is a sphere. Although earth is not a perfect sphere, but for the matter of understanding here, we will say that it is a sphere. So mathematically, how is a sphere generated? Let's try and understand that. So in mathematical terms, a sphere is obtained when a plane circle is revolved around any of its diameter. So let's consider this circle that we have in front of us. The center is O, as you can see. If we have any of the diameter, there are tons of diameters, infinite number of diameters that a circle can have. I'm just taking the vertical diameter here, and if we revolve it around that diameter, the solid that is created is the sphere of that particular circle. Now in place of that, we can take any other diameter as well. If I just take any other random diagonal diameter, this one, and if I rotate it, revolve it rather, if I revolve it around that particular diameter, then the solid generated is again the same sphere. If you notice, the original sphere and this sphere is absolutely same. Now, after understanding what a sphere is in the solid form, let's have a look at the important formulae that we should know for the application sake in problems. So here are the two important things. The first one is the volume of the sphere. Now, as we had talked about the circle that we started with, if the radius of that circle is r, then the radius of this sphere will also be r, right? Because radius is nothing but the length from the center of the sphere or the center of the circle to any of the point on the sphere. So the length of the segment that connects the center of the sphere to any point on the sphere is nothing but the radius r. So using that r, we will have the formulae of the volume and the surface area of the sphere. So here they go. The volume of the sphere is 4 by 3 pi r cube. The derivation of this, not in the scope of this book right now, although we would need integration formula for that, which we might be learning in the further standards, but for now we should understand that the volume of the sphere is 4 by 3 pi r cube, and secondly, the surface area of this sphere. Now surface area is the entire area at the outside of this solid, and the formula for that surface area of the sphere is 4 pi r square. So these are two very important formula when it comes to applications of spheres. Volume of the sphere with radius r is 4 by 3 pi r cube, and surface area is 4 pi r square. Now, after understanding this, let's turn our attention to an extension of spheres, and that is called a spherical shell. Now it's a very simple concept to understand. We call it an hollow sphere as well. One thing to understand, don't get confused by the word hollow here. When we were talking about a hollow cone, we understood that the hollow cone is nothing but where there is absolutely hollow inside the cone. There is nothing here. Here, when we are talking about a spherical shell, the sphere is going to have certain thickness. Think of it in this way. We have a sphere of radius r. We have a larger sphere of radius r. Now, we have a smaller sphere of radius small r. Now, if I coincide the centers of both these spheres, so if I put this smaller sphere right at the center of the larger sphere and eliminate that volume, then the remaining volume, the remaining solid that we get is a spherical shell. So you will clearly understand that this spherical shell will have a certain thickness, as you can see in the figure. So basically, the inside of this spherical shell is not accessible because it is the inside which is hollow, but this shell is going to have a certain thickness, and that thickness is going to be the radius of the larger sphere minus the radius of the smaller sphere, and hence the thickness of this spherical shell is going to be capital R minus small r, where capital R is the radius of the larger sphere and small r is the radius of the smaller sphere. Now again going forward to two important formulae here, rather three. Firstly, the volume of this spherical shell is simply going to be the volume of the larger sphere minus the volume of the smaller sphere, and that is going to be 4 by 3 pi capital R cube minus 4 by 3 pi small r cube. So it is very obvious how did we derive this. It's just simply that the volume of the spherical shell is volume of the larger sphere minus volume of the smaller sphere, and we used the original formula of volume of a sphere and applied it there. So we got 4 by 3 pi bracket capital R cube minus small r cube. All we did was took 4 by 3 pi common, and then we had capital R cube minus small r cube in the bracket. So this is the volume of the spherical shell. Moving forward, there will be two surface areas for this spherical shell. One is the outer surface area and one is the inner surface area. Very naturally understood, because this spherical shell has an outer body and an inner body, right? So the outer surface area is going to be 4 pi capital R square, and the inner surface area is going to be 4 pi small r square. So these are again a couple of important formulas for the spherical shell. We learnt about sphere in this section, we learnt about spherical shell in this section. Further, we are going to talk about hemispheres and hemispherical shells. Friends, further let's talk about something called as hemisphere. Now, as the word suggests, hemisphere is nothing but half of a sphere. Earlier we learnt what a sphere is. A sphere is a solid which is generated by revolving a circle across its diameter, any of its diameter for that matter. So if this is a sphere, hemisphere is nothing but exactly half of it. So what we are going to do is cut this sphere exactly from between. So basically we are going to use any of its diagonal. We are going to cut it half from any of its diagonal, using any of its diagonal, which will pass through the center of this sphere, and the resulting solids, rather we are going to get two solids which are going to be exactly equal to each other, and both of them are going to be called as hemispheres. So basically one sphere when cut into two equal halves is called as a hemisphere. Each of them is called a hemisphere. So let's just consider one of it. Let's just eliminate the second thing. This is a hemisphere. So talking about the radius of this hemisphere, it's going to have the same radius as that of a sphere. So if a hemisphere has a radius of r, so let's try and understand what are going to be the formulae which we are going to utilize, starting with the volume. Now the volume of a hemisphere is very easy to calculate, because we know that the volume of a sphere is 4 by 3 pi r cube, and since this is exactly half of that, so the volume of a hemisphere is going to be half of 4 by 3 pi r cube, and hence the volume of a hemisphere is equal to 2 by 3 pi r cube. So this is one very important formula for the hemisphere. Secondly is the curved surface area. So now a sphere has a surface area which is the outer surface area, because a sphere has an outer body, right? Inside it's a complete solid. So when we talk about surface area for a sphere, it is 4 pi r square. But if you notice, a hemisphere has a curved surface area plus it has a base area as well, because when you cut a sphere into half, you are exposing one base circle as well. So firstly, the curved surface area of a hemisphere is half of the surface area of a sphere. So that is going to be half of 4 pi r square, which is going to be 2 pi r square. So the curved surface area of a hemisphere is just 2 pi r square. But when we talk about the total surface area of a hemisphere, it is equal to this curved surface area plus the area of the base, and hence the total surface area of a hemisphere is equal to 2 pi r square plus pi r square, making the total surface area of a hemisphere is equal to 3 pi r square. So these are the important things that we should know about a hemisphere. One, that the hemisphere is nothing but exactly half of a sphere. Two, the volume of a hemisphere is half that of a sphere, which is 2 by 3 pi r cube. Three, the curved surface area of a sphere is half of that of a sphere, which is equal to 2 pi r square. And lastly, the total surface area of a hemisphere is equal to the curved surface area of a hemisphere plus the base area, which is equal to 2 pi r square plus pi r square, which is equal to 3 pi r square. Now, understanding about hemisphere, let's turn our attention to a further extension of this, which is the hemispherical shell. Like we talked about a spherical shell in the last section, here a hemispherical shell is nothing but a hemisphere inside a hemisphere. So basically, one small hemisphere is removed from a larger hemisphere to create a thickness and hence create a shell. So if I try and see this, if I rotate this 180 degrees, you will understand what a shell means. This is an exact shell which has a particular thickness and which is hollow from inside. So this is a hemispherical shell. Let's say the larger hemisphere has a radius of capital R, the smaller hemisphere has a radius of small r, right? So the smaller hemisphere has been removed from the larger hemisphere, and the shell that creates has a thickness now of capital R minus small r. Like we studied in the spherical shell, even the hemispherical shell has a thickness of capital R minus small r. Moving to the volume of this hemispherical shell, it's naturally going to be the volume of the larger hemisphere minus the volume of the smaller hemisphere, and that is going to be 2 pi capital R cube, rather 2 by 3 pi capital R cube minus 2 by 3 pi small r cube, further which can be simplified as 2 by 3 pi into capital R cube minus small r cube. So this is about the volume. Further, let's talk about the surface areas. One, there is an outer surface area which is naturally going to be 2 pi capital R square, because we know that for a hemisphere the curved surface area is half of that of a surface area of a sphere, which is half of 4 pi r square, and hence 2 pi r square. So the outer surface area for a hemispherical shell is 2 pi capital R square. The inner surface area for a hemispherical shell is 2 pi small r square. Now hence, after talking about the outer and inner surface areas, if we talk about the total surface area of a hemispherical shell, you can see that it is nothing but the outer surface area plus the inner surface area plus the area which the thickness has, which the ring has basically. So we have to account for that. So while accounting that, here goes the formula for the total surface area, which is 2 pi capital R square plus 2 pi small r square plus the area of that ring, and the area of that ring is nothing but pi capital R square minus pi small r square. Reason being, if you have a look at that base, it is a larger circle minus the smaller circle. So when you talk about the area of that base, it's the area of the larger circle minus the area of the smaller circle, and hence pi capital R square minus pi small r square. So when we look at this total surface area in its entirety, it is 2 pi capital R square plus 2 pi small r square plus pi capital R square minus pi small r square. So simplifying this, you will get the TSA or the total surface area as 3 pi capital R square plus pi small r square. And hence these are the important formulae about a hemispherical shell with an outer radius of r, capital R, and a smaller radius of small r. And the formulae are: the thickness of this shell is capital R minus small r. 1. Volume of the hemispherical shell is 2 by 3 pi capital R cube minus 2 by 3 pi small r cube. 3. The outer surface area of this shell is 2 pi capital R square. 4. The inner surface area of this hemispherical shell is 2 pi small r square, and lastly, after calculating, the total surface area of this hemispherical shell is 3 pi capital R square plus pi small r square. You don't need to remember all these formulae though, but if you have an understanding of how exactly, rather first what these things are and how exactly these are created, then getting these formula is a piece of cake if you understand them well and you can visualize them well. So on this note, let's move on to a few problems on the basis of the concepts that we have learned, and after that we'll move our attention to the miscellaneous examples of this chapter. We'll have a mixed bag of questions dependent on the concepts that we have learned entirely in this chapter, starting from cone to the frustum and then all different kinds of spheres.